In an attempt to understand how nature works, its fundamental constituents, its motion and behavior through space and time, and the related entities, human beings have made several successful attempts in the realm of science and technology. General theory of relativity, quantum mechanics are the two pillars of these monumental achievements, followed by string theory, which is still in its nascent stage. In today's video, we are going to look into these three pillars of modern physics: when, where, and how it all started, its progress, developments, some deep philosophical questions, and most importantly, its limitations in our understanding of space and time. For this video, I am leaving the mathematics part aside, as this is going to be a fascinating journey from the very big scale of cosmology down to the most fundamental subatomic level. My name is Shaunak and you are watching this video on my channel Physics for Students, and a warm welcome to watch this video. So before we go ahead and dive into this fascinating journey, let us quickly look into what are the topics that we are covering today. So we are starting with the physics which existed during the time of 1905 to 1916, the relativistic world. What is the paradigm shift that happened from relativity to geometry? Einstein's field equations and its understanding in the nature and gravity of space-time and space-time curvature. The macroscopic world of determinism, what really happened in 1911 at Brussels, Belgium, the first Solvay Conference and the first quantum meet, the probabilistic world of quantum physics, the unification of forces, and string theory. These are more or less the topics that we are covering today, and you can just relax this video because it is not going to be too much of equations and mathematics. You can relax with a cup of coffee and just enjoy this fascinating journey, answering some deep philosophical questions and giving you a complete perspective of modern physics. So we first start with the physics that existed around 1905 to 1916. Why am I taking this genre? We will come to understand there's something really significant happened, and there was a significant paradigm shift in human thinking. And what was that? That is coming up in this part of the video. So during that time when we are talking, the system of physics existed what is called a classical system, a relativistic system, and a quantum system. Classical system, as we know, started from the genius Newton, or even earlier to that Galileo and Copernicus, is absolutely deterministic in nature. That means given initial conditions of a particular system, if we can proceed according to those given conditions, we can predict the future, we can say what that particle will land up to, or any movement which is determined by Newton's laws of motions. Well, the relativistic system, which started with Einstein's special theory of relativity and further into general theory, is also deterministic in nature. However, the quantum world is probabilistic in nature. Now, what do we mean by that? I hope you all understand, but still we will get a good glance over that so that the understanding is much more profound. So a classical system which started with Philosophiae Naturalis Principia Mathematica, a foundational work in terms of physics, and which changed the entire course of the thinking, is being guided by Newtonian mechanics. Relativistic system, which consisted of special and general relativity, is also considered to be a geometry of space-time. However, it falls within the realm of classical system. Quantum system is something which is, I would say, probabilistic. It is not deterministic. It contains a lot of chances. These are being guided by wave function. Now, in my other channel, General Relativity Explained, you can watch out my recent video which tells the philosophy of general relativity, where I have gone a little bit more in explaining those areas which I'm not doing in this video, because this video aims to be something different. However, if you really want to know more about the philosophy of general relativity, you can go to my other channel, which is General Relativity Explained, given in the description box. Now, when we talk of the consequences of relativity, we get the special theory of relativity, particularly deals with relativity of simultaneity. By simultaneity, I mean that certain events which are occurring simultaneously in the nature of space and time. We also get length contraction, time dilation, relativistic mod, the universal speed limit, that is the speed of light, and the mass energy equivalence. These are some of the consequences of special relativity, and most importantly, if I take starting from relativity of simultaneity to universal speed limit, you will see that the relativity is more relativistic in nature, and this is being guided by Lorentz transformation. And because it is being guided by Lorentz transformation, the entire working of the mathematics is linear in nature. Because it is Lorentz transformation, because it is linear in nature, so that is why you will see that the conceptualization of special relativity as well as the mathematics is much easier considered to the next which is coming up. So what I am trying to make a point over here is that special theory of relativity, the entire consequences reaches more on the relativistic effects, and that is why these are linear in nature. Now when we talk of the consequences of general relativity, we get gravitational time dilation, gravitational waves, frame dragging, black holes, singularities, and horizons. If I take all these areas which is marked in red, these are covariant in nature. Now if you're really curious in knowing what is covariance, then you can go to my other videos in general relativity, where I have really dealt in details what is covariant and why do we need tensors. However, just to give you an idea that covariant in nature means that these are non-linear in nature, so it won't be linear. That means it varies according to certain guided routes. So what I'm trying to make here a point is that, as you see from special relativity, as we move to general relativity, the entire scenario changes. From Lorentz transformation we get into covariance, and that is why the mathematics and conceptualization of GR is much more challenging, because it is non-linear in nature. Now if we consider the relativistic effects of special relativity, which we just saw, those time dilation and length contraction, when Einstein generalized to accelerating frames of reference, because these were non-accelerating frames of reference as we all know, it went into something which is called a curved space-time. And this curved space-time had a huge paradigm shift in terms that we understood relativity less and geometry more. We also got into a complete change in mathematics, because tensors and differential geometry, even it was not known to Albert Einstein, who fetched help from some of his friends like Michel Besso, Marcel Grossman, and tensor was independently developed by Tullio Levi-Civita and other mathematicians in the other part of the world. So it is a huge change, because we are not anymore dealing with relativistic effects. The mathematics is not Lorentz transformation, but mathematics is totally geometry, which relies upon differential geometry, tensors, and various other exotic mathematics. And we also understood that there is a complete understanding, a change in understanding in terms of coordinates. The relativistic effects of simultaneity now got changed into different kind of coordinates. Tensors came into, and now we are now really much more into the geometry part. We are not dealing with much of the relativistic part. This is one of the first fundamental realization when we generalize special relativity to geometry, that we are not dealing with relativity anymore, but we are dealing hugely with geometry, different type of mathematics, which was even not known to Einstein during that time. So there is a huge paradigm shift. Now the question that lies is that these type of paradigm shift which happen from relativity to geometry of space-time, what was the underlying, or what I would say is the main guiding force of this kind of a paradigm shift? Let us find it out in the next part of our video. So it is called the Einstein's field equations, although it requires several videos, and I have got several videos in my playlist. Here I would like to just give you a basic overall bird's eye view on Einstein's field equations. This is called the macrocosm of predictability, because we are falling into the classical arena, but on a much more higher macrocosmic level. So that is what I was talking, that it is more of a geometry rather than relativity of simultaneously. It deals with the geometry as the intrinsic nature of space-time rather than something extrinsic. This is very important because we will soon discover in our video that why the intrinsic nature of space-time is so important. So all those mathematical tools that we require, parallel transport, covariant derivative, Christoffel symbols, geodesics, everything, these are required to understand geometry better, to understand the curvatures, to have a more intuitive nature in terms of understanding, and we require a lot of exotic mathematics. These are the mathematical tools which were developed and used by Einstein in order to get a better understanding of the nature of space-time. And that is why his magnum opus, general relativity, is more of a geometry rather than relativity. So these are used to understand the curvatures and the intrinsic nature of space-time. So all these things, the length contraction, time dilation, transformation of Maxwell's equations, and if you consider on the right hand side the aspects of general relativity, tensors, geodesics, parallel transport, Riemann curvature, curvature tensor, all these shows that we are now moving ourselves from relativity to geometry, and we have less relativistic effect and more of the nature of space-time. Because none of this you see on the left hand side, those in orange, the length contraction, time dilation, and the transforming of Maxwell's equation has absolutely no relation with geodesics and parallel transport and curvature tensor, all those things. These are exclusively, those points written in green are something which deals with the nature of space-time. So it is less of relativity and more on the geometry of space-time. So this very equation, quite known to you, is actually the underpinning force of guiding the nature of space-time. So this left-hand side part, it actually measures the curvature of space-time, that is the geometry of space-time, and this one deals particularly with the matter content of space-time, and it actually shows the matter movement, and both of them are equal. So the geometry of space-time is equal to the matter movement. We will just quickly go ahead and understand what those Greek hieroglyphics actually mean, so that this understanding is much more better. So we would like to demystify the equation, and we are not going to go much more into the mathematics. We'll just touch base what those equations look like. So the first R, which is called the Ricci curvature tensor, it actually measures how the volume of matter changes when it moves from flat space to curved space. The next R is called Ricci scalar, which keeps track of how the size of a ball deviates from Euclidean space to non-Euclidean space. This G is basically the metric tensor. The lambda is the cosmological constant, and the metric tensor is actually the way of measuring distance and all the causal structure of space-time. The next one is this T is called the Riemann. Sorry, this is the Riemann curvature tensor. This T is missing. This is the Riemann curvature tensor, which is somewhere hidden in this Einstein field equation. You can go to my playlist in general relativity and you will understand that I've got a completely different video explaining on Riemann curvature tensor, which is actually a kind of a shortening of the Ricci curvature tensor. I'm not going into the details, but Riemann curvature tensor is hidden, which describes the curvature of Riemannian manifolds. This T is actually called the stress energy momentum tensor, and it shows the matter movement through space-time. The lambda is the cosmological constants. 8 pi is derivation which comes from Poisson's equation. G is the good old Newton's gravitational constant, and c raised to the power 4 is the dimensional analysis which shows the speed of light. So these are some of the components which quickly explains, so that when you next look into this, it doesn't come something as Greek hieroglyphics. So as we are dealing with the curvature of space-time, there is a concept which you all know is called geodesic. So a straight line, when it is predicted over a tram line, actually takes a kind of a curvature. So it generalizes the notion of straight line into curved space-time, and this is curvature is due to this gravity is due to space-time. So when an object moves through space-time in a straight line, which is technically called a geodesic, but if the space-time is curved, the line will definitely follow the curvature and it will change the direction. And this changing of direction or the curvature is what we call gravity, and that has been duly emphasized and detailed out in Einstein's field equations. So when we talk of geodesic, if we take a kind of a sphere, and these are the people, you see they are going in a direction that they will meet somewhere. So this is, yes, they meet at the North Pole. So this is called what is called a positive geodesic. So this is one, you see the blue lines are meeting and this line is basically curved and the great circle shows this. So this is the great circle. So the shortest path between 2 points on a surface is called a geodesics. Geodesics are trajectories of the moving bodies under the influence of gravity, because it is the gravity which is the curvature which is responsible for what we know as gravity. So the Einstein field equation actually tells us the geometry of space-time to the distribution of matter within it. And just the way electromagnetic fields are related to the distribution of charges and currents via Maxwell's equations, the Einstein field equation relate the space-time geometry to the distribution of mass, energy and momentum, that is, they determine the matrix tensor of space-time for a given arrangement of stress, energy, momentum in this space-time. I'm not going to explain what this actually internally means, because there will be a lot of mathematics, a lot of time will be required, but let us understand that Einstein field equations relate the geometry of space-time to the distribution of matter within it, and it relates the geometry to the distribution of mass, energy, momentum and stress. Now the question that rises is that the Einstein field equation describes how energy, momentum cause curvature, and curvature itself is determined by the metric. So the field equations are actually a set of extremely complicated nonlinear second order partial equations. In order to find an exact solution, in most of these cases it is almost next to impossible. So because the equations determine the metric depending on the energy content of the space-time, they are huge. I mean to say, if it was possible, I would have shown actually when it is expanded how it looks like. But this is obviously huge, and in most cases, finding an exact solution is not possible. So question is that if it is so complicated, it is so difficult, it is so big, so monstrous, then what is the use? So if we use the Einstein's field equations in this type of a scale, say for example, a person standing on a particular, on the surface of the earth, or people standing around here or anything, the question is that will it actually make any change? Can we use Einstein's field equation to calculate the curvatures? This one. So the answer is yes, but the effects would be too low to notice. Yes, because the Einstein's field equations are used mostly in bigger cases, for example, Jupiter, Sun, or in case of calculation of black hole. So definitely we can use Einstein's field equations to calculate things like a person standing on a surface of Earth, or minimal pressure put upon, but it would be too low so that we cannot use that. Now, up till now, we were moving into the realm of Einstein's field equation, how it all started, the general relativity, from special to general, etc. But we will take a pause now and we will move back by a certain number of years, and we would like to visit, okay, so the black hole is also there, right? And we would like to visit a place which is far, far, far off from where Einstein was doing all his calculations. And let us turn the pages of history now and move into 1911 at Brussels in Belgium. So here you can see the name of this person. There was a businessman in the name of Ernst Gaston Joseph Solvay, and he was born around 1838 till 1922. He was basically a Belgian chemist, industrialist and philanthropist. Born in Rebecca, he was prevented by his acute pleurisy from going to university, and he worked in his uncle's chemical factory from the age of 21. In 1861, along with his brother Alfred Solvay, developed the ammonia soda process for the manufacturing of soda ash from brine and limestone. He founded the companies Solvay and Sai and established his first factory in 1863 and further perfected the process until 1872 when he patented it. Soon Solvay process and plants were established in the United Kingdom, United States, Russia, Germany and Austria. Today, around 70 Solvay process plants are still operational worldwide. The exploitation of his patents brought Solvay quite an amount of money, which he used for philanthropic purposes, including the establishment of 1894 of the Institute for Sociology at the Free University of Brussels, as well as the International Institutes for Physics and Chemistry. In 1903, he founded the Solvay Business School, in which is also a series of important conferences in physics known as the Solvay Conferences, whose participants included Max Planck, Ernst Rutherford, and other eminent scientists. Now, this is the famous Hotel Metropole today, where the first Solvay Conference took place, and this is the kind of a postcard way back in 1920. Now, why I'm mentioning the first Solvay Conference and all those, it will soon be clear. Now, in his letter of invitation dated June 15, 1911, Ernest Solvay explained that he conceived the first meeting as an international scientific council to elucidate some current questions of molecular and kinetic theories. Hendrik Lorentz was the chairman of the first Solvay Conference on Physics held in Brussels from 30th of November to 3rd of November 1911. The subject was radiation and the quanta. This conference looked at the problems of having two approaches, namely classical and quantum theory. The first Solvay Conference is considered as a turning point in science when classical physics was about to give way to quantum theory, forever changing the way we look at space and time. So I have made a complete different video on first Solvay Conference, rather Solvay Conferences. You can look into my channel. It is much more detailed on all the photographs and the details of this. This is the famous photograph of the first Solvay Conference, and there were included 24 participants, all based on invitation. And you can see here Anton Lorentz, you can see Einstein, you can see Rutherford, you can see Marie Curie, you can see Avi Poincaré. Almost entire world of physics and mathematics and chemistry are around here. This person, Ernest Solvay, was not present in the particular meeting, and that is why his head has put into this photograph superimposing, and it appears to be quite big. Now, the first quantum meet which took place is extremely important. The reason is that this is the first conference which took place by invitation. Einstein made his debut to the non-German speaking community. That means his relativity was mostly in German and it was confined to the Germanic people. And this is the first time when Denmark, French, France, including Germany, Austria and England even, they participated. And also this is the first time when classical physics and quantum theory was discussed at large right on the desk, and the duality of wave particle and discrete quantum theory was brought into it. This is considered to be a turning point for modern physics. The quantum theory first came up front, and there was a curious letter of recommendation because Einstein wanted to go back to Zurich and find out a job. And Ernest Solvay first made the declaration that from now on the entire conference would be sponsored by him. And if you see my other video in first Solvay Conference, you will understand that the 2022 dates have also been declared. So it has been going for almost more than 70 plus years. The fifth Solvay Conference, which took place in 1927, is considered to be one of the most intelligent picture ever taken. And you can see out of those 27 participants, 19 of them were awarded or to be awarded Nobel Prize in Physics. So this was the conference which took place, and after that there was a kind of this was a delay because of the First World War, and this is the place where it took place. So the importance is that the subject was electrons and photons. So you understand that quantum mechanics has started to take its place. Einstein remarked first that God does not play dice. We will soon look into what is the meaning of that? And Bohr replied, Einstein, stop telling God what to do. And 17 of 20 participants were or became Nobel Prize winners, and this is considered to be the most important decision on quantum theory. The reason behind this is that the electrons and photons are being discussed. The quantum probability and the probabilistic world is now coming in front. As you can see, that classical mechanics is slowly fading away, giving rise to another revolution in terms of physics. So now we enter into the quantum world, and what we find is that in a quantum world, these people, starting from Descartes to Galileo to Newton, then to Faraday, Maxwell, and Albert Einstein, we now are moving into the world of probability, which is being ruled by Feynman, even Einstein, Max Planck, Heisenberg, Born, and all those people. So here nothing is definite, but here is a probability, and there is a chance, and there is a range and distribution. So we are not moving into a probabilistic, into a classical world, but rather we are taking a quantum leap from the classical world into the quantum world, where there is nothing as definite as it is possible, but something which has got a range and a distribution and a probability. Now, what do I mean by that? Let us quickly understand. So the classical world is moving into a quantum world. The deterministic world is going to a probabilistic world. The certainty is going into uncertainty, and the common sense, the way we think, is devoid of common sense. So what we are looking now is a complete paradigm shift. So I won't be explaining the postulates of quantum mechanics, but just to give you an idea that the postulate of wave function, or the first postulate, it shows that the state of a quantum mechanical system is being dominated by what is called a wave function. You can ignore those integration and psi and complex conjugate, all those signs, but just to give you an idea that this actually shows that the entire world of quantum mechanics is dominated by wave function, which only gives you a probability of understanding where the location, position, momentum of a particular subatomic particle can be or cannot be. So we enter into the world of probabilities, and the world of probabilities is probabilistic in nature. So it is impossible to predict the outcome of a single experiment. Only thing that we can predict is the probability of detecting each system. So if we get this kind of a wave which is moving in this direction, so that there are particles, it will probably land 42% here and 58% here. And that is why there is a chance, and in a letter Albert Einstein wrote that the theory says a lot but does not really bring any closer to the secret of the old one. I at any rate am convinced that God or he does not play dice. So the first Solvay Conference, which gave rise to a new revolution, which is the probability and quantum mechanics, is now shaping its way through the annals of history, and our dear old Dr. Albert Einstein is at all not liking this, and that is why he made the remark, God does not play dice. So this is important in our understanding of nature of space-time, that the probabilistic nature of the world is now taking its shape, moving away from classical physics. So there is something also which is called a superposition, that an electron is simultaneously in all the locations covered. So here you can see the classical system, either this blue or the electron can be outside the box or inside the box, but here it is both inside and outside. So if you throw a coin up in the air, when it is in the air, it is in both head and tail conditions, but it falls down, it takes one position. That means it is either head or tail, which is being famously described by Schrodinger's cat, which tells that cat is both dead and alive. We also find that there is a wave-particle duality. J.J. Thomson won the Nobel Prize in Physics, providing electrons are particles, and his son George Thomson won the Nobel Prize in 1937, proving electrons and waves. Now, father has proved that electrons are particles, son has proved electrons are waves. Who is correct? The answer is both of them are true, and that is why we call that the nature of quantum mechanics is very weird. So every particle or quantum entity may be described as either particle or wave, and here it is again We have two contradictory pictures of reality. Separately, neither of them fully express the phenomena, but together they do. That is, if you take things separately, it won't explain, but together they would do. So we get a kind of a wave function. So classically, if you get two particles, position and time denoted by x and t, then possibly there is a particular numerical value in the Cartesian coordinates through which we can find it out. But if we get a kind of a wiggling wave like this, so the particle can be here, it can be here, it can be here, it can be here. So what is happening is that this type of probabilistic nature is being denoted by the Greek letter psi, which tells that it is a variable quantity that mathematically describes the wave characteristics of a particle. And also the value of the wave function of a particle at a given point is related to the likelihood of the particles being there in time, and you square it, and that is called the probability density in order to find it out. More are there in my playlist in quantum mechanics. You can find it out. Just to cut short in a nutshell, what we are trying to make a point is that the deterministic world of classical physics, where everything is certain and probably we can even predict the future, is not here. So the particle can be here anywhere, or it can be simultaneously at both the locations, and that is why we try to find out only the probability. So the Max-Born statistical interpretation shows the probability of finding the particle of x and dx plus dx at time t. So if you get a kind of a wave distribution like this one, then we get quadrants like A, B and C. Then if this is dx, then there is a high probability that we can find the particle around this A region and not, most importantly, around B and C. So this is called the indeterminacy in quantum mechanics, and that is why Einstein made the famous quotation, or famous remark I should say, God does not play dice. That means there is no chance, it should be definite. Now all these things that we have been talking, the wave-particle duality, quantum superposition, probabilistic nature, Heisenberg's uncertainty principle, wave function and a lot more, ultimately leads to a probabilistic, non-deterministic world of chances. Now we have seen one part of the history where physics is being dominated by classical era. Then we moved into relativistic world, which is also classical and deterministic. Then we found the Solvay conferences, which shaped the world of history or the nature of history into quantum mechanics. Now we find that the quantum mechanics is somewhere in between the probabilistic world and the deterministic. Now the question is that, is there a possibility to unite both of them? In order to understand, we have to quickly turn the pages of history, and then we come into the summer of 1960 and 68, where some physicists were trying to unify both those theories. So the unification of forces was basically done in order to unify gravity, electromagnetism, strong and weak force. Now I won't be explaining all those because this is something you already know. So the problem was that the strong force were carrying the carriers called gluons. Weak force already have W and Z bosons. The electromagnetic force well being explained by photons, but gravity was unable to find a place in the standard model of particle physics. So the physicists named them as gluons or WZ bosons, and for gravity it was named as gravitons. But the question is that till today, when I'm making this video, there is still a search for gravitons. So here is a standard model, and this part is the electromagnetism, this is the strong, and these two defines the weak force. But we are unable to find out the place for gravitons. And that leads to the next part of our video, when there was a time when the unification of forces were being attempted. Now string theory, as we call it now, was first studied in the late 1960s as a theory of the strong nuclear force. The strong force or strong nuclear force is one of the four fundamental forces of nature. As the name suggests, the strong force is the strongest forces of the four. Now here is the gentleman Gabriele Benziano, the Italian scientist, around this time discovered a mathematical formula that had many of the properties that people were trying to incorporate in a fundamental theory and strong nuclear force. This formula was kind of pulled out of the blue, and ultimately when Ziano and others realized within a couple of years that it was actually describing quantum theory of string, a one-dimensional extended object. So the quantum electrodynamics, or QED, is the relativistic quantum field theory of electrodynamics. In essence, it describes how light and matter interact and is the first theory where full agreement between quantum mechanics and special relativity is achieved. Remember that the quantum electrodynamics is the theory which unifies special relativity and quantum mechanics, but not with general relativity. It was later being abandoned in favor of quantum chromodynamics, the theory of the strong interaction between the quarks mediated by gluons. Subsequently, it was realized that the very properties that made string theory unsuitable as a theory of nuclear physics made it a promising candidate for a quantum theory of gravity. If you really want to know more about quantum theory of gravity and string theory, go to my playlist String Theory. I've got 2-3 videos made on details about that. So this is the quantum theory of gravity, and we are into the arena, into the time of physics, into the history where there is an attempt to find out a unification of forces. Could we find out? Let us see in the next part of our video. So the earliest version of the string theory was called Bosonic string theory, developed around 74 to 84, incorporated only the class of particles known as bosons. So these two gentlemen, John H. Schwarz and Joel Shirk, studied the boson-like particles of string vibration, and their properties exactly match those of the graviton. So the gravitational forces, that is the hypothetical messenger particles. Schwarz and Shirk argued that the string theory had failed to catch on because the physicists had underestimated its scope. But there were problems. The problem was that it had a critical dimension of d equals to 26. The theory has a fundamental instability in the presence of tachyons, and most importantly, while bosons are critical ingredient of the universe, they are not only the only constituents. They do not take into account what are called the fermions. So the superstring theory, which developed around 84 to 94, was in an attempt to unite both boson and fermion. And there is something which is called supersymmetry, and this was developed. Why? Because there was an inconsistency in the standard model. So between fermion and boson, as you see, there was a symmetry, and supersymmetry actually included supergravity, quantum field theory, and gravitational force. More of these are there in my video in string theory. You can go into my playlist and find it out. So this was basically an attempt to unify quantum physics and general relativity, an attempt to unite the very small with the very big, that is the microcosm with the macrocosm, and with the world of chances with the world of predictability, or something which we call determinism. So now that we know that something new has cropped up, it is time to reframe the system in physics. So we get a classical system, we get another classical system, that is relativity, and we get a quantum system, and we get something which is classical plus quantum, which is the string theory. Now, as you see that there are certain needs for extra dimension in string theory, because Einstein theory of relativity explores nature into 4-dimension space and time. This is given a kind of a mass we call a curvature, and this is which is explained in Einstein's field equations. But if we get a same kind of a 4-dimension and we use those wiggling strings, then we are unable to find out the fundamental particles, that is neutron, proton, electron, or so on. Why? Because there is a lack of space. So in order to vibrate these gravitons or strings, in order to produce those fundamental particles which will help us to define the nature of space-time, we required additional space. And this space was actually given through this, that we get particle 1 in dimension 1, particle 2 in dimension 2, and 3, 4, and so on, and maybe 11th dimension particle. So the Bosonic theory actually predicted that there should be 26 dimensions, while the superstring theory predicted something which is 10 dimension, and then M theory is something which predicted 11 dimension. However, there were two gentlemen who made significant contribution in this extra dimension. One was Theodor Kaluza and Oscar Klein. Now, Kaluza added a special twist to that fifth dimension, making it wrap around itself, which he called cylindrical condition. Here it is. So this requirement made something new pop up. Kaluza recovered the usual equations of general relativity in the usual 4-dimension plus a new equation that replicated the equations of electromagnetism. So a decade later, physicist Oscar Klein tried to give Kaluza's idea an interpretation in terms of quantum mechanics. He found that its fifth dimension existed and was responsible in some way for electromagnetism. That dimension had to be scrunched down, wrapping it back itself down to almost 10 to the power minus 35 meters. So a standard analogy, as you see in a multidimensional object, is a garden hose. If the hose is viewed from a sufficient distance, it appears to have only one dimension, its length. However, as you approach closer and closer, one discovers that it contains a second dimension, its circumference. Thus, an ant crawling on the surface of the hose would move into 2 dimensions. So the larger dimensions are in this way, and the compact dimensions are basically curled up into something which we call compactification. Now, what do we mean by compactification? Let us see in this part of our video. So this is what is called M theory, and M theory is basically the compactification where this type 1, type 2, etc. compactify. So here you can see, if you want to find more about M theory, what are type 1, type 2A, you can still look into my string theory video. So the idea of M theory is to bring the 5 versions of string theory together. Some of the extra dimensions can be thought as curled up into spirals. M theory would need 11 dimensions to string theory to unify. Each basic particle is created at the most fundamental level, as I was telling, by vibrating strings in different dimensions. So as you see, this is a very important note that the nature of the gravitational interaction, in particular the equivalence of the gravitational and inertial mass, which allows to represent gravity as a property of space-time itself rather than a field propagated in a space-time background. So gravity is most important as a property of space-time. It is not a field just like other which is propagating at the back. So the search for M theory, search for 11 dimensions is still on, and we are sure that in due course of time, the way mathematics and physics and science is progressing, we would be able to find it out. But still now we have got no direct evidence or experimental evidence even in the Large Hadron Collider that this type of dimension or this type of particle exists. So that's all for today's video, and I would just like to summarize what we have learned. We looked into the classical world of relativity. From relativity we moved into geometry, the components of field equations, the curvature of space-time, the world of determinism, and how the Solvay Conference paved the way for quantum mechanics. We entered the realm of quantum mechanics, and then we tried to attempt to unify quantum world with the general relativity world. String theory came, but there were limitations, there were need for extra dimension, and we are still searching for M theory. So this is a kind of a quick tour, a kind of a quick, I would say, historical or scientific perspective on quantum mechanics, general relativity, and the still ongoing researches on string theory. I hope you like this video. Please put up your comments, and please like, subscribe, and click on the bell icon to get all the notification from Physics for Students. And I will be soon back with some more interesting videos on Physics for Students. So don't forget to subscribe and like to my channel. This is Shaunak signing off from Physics for Students as of today, promising you to be back very soon. Till then, best wishes, stay safe, stay healthy, and keep on learning physics and mathematics. Thank you very much for watching this video.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment, or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram, and LinkedIn. See you soon in the next video.